All right, morning everyone. So today I will introduce Lorentzian polynomials, and thanks Chris for giving us some motivation. Yeah, but before we get there, I want to start with a theorem of Newton because I want to motivate studying these ultra log-concave inequalities. So there's a nice theorem of Newton. Say let O1 through Rn be real numbers. And then you look at the elementary symmetric functions. So the E1 is going to be just the sum of them. And E2 is sum of product of two at a time. And E3 is three at a time, and so on, right, up to the n, which is product of all of them. Okay, so these are elementary symmetric functions. And Newton said, assuming that all the e's are positive, assuming if all the they satisfy the following ultra log-concave inequalities. So you just take these and you look at the averages. So you do look at EK divided by n choose k. And you compare this to k minus 1 divided by choose k minus 1 times ek plus 1 divided by n choose 1. And we have this type of inequalities. Okay? Because when all the r's are 1, then this is 1, because they're going to 1, obviously true. Okay. But so you're going to prove this in the exercise. So another way to think about this is that notice that if I have a polynomial, right? So if I look at the polynomial x plus r1, x plus r2, and so on, x plus rn, right? These e's are the coefficients of this univariate polynomials, right? So what this is saying is that if this polynomial has real roots, right, and positive coefficients, then the coefficients satisfy this Newton's inequality. Okay, so this is called Newton's inequality. Inequalities of this type are called Newton-like inequalities. So instead of the EIs, we're going to be studying which sequences satisfy this type of inequality. So right, this denominator dividing is sort of, and you can see that it is natural to do so. And then so let me recap last time what we did. So I heard that yeah, some people may have gotten a little lost at the end, so let me recap a bit. So last time we introduced matroids, and then we introduced matroids and basis generating polynomials. Of a matrix, right? And then we also look at this property, what I was calling negative dependence. Yeah, so I should warn you that if you try to look this up in the literature, negative dependence is more of a general term that can mean many different things. And the last time I was using it specifically to look at the probability, you're in a matrix, you are pulling a basis uniformly at random, right? So we're comparing probability that's I is in B times, J is in B, right? Comparing that with, probability that both I and J, I and B, and then what I want. Yes. So, but in the literature, negative dependence means many different things. Okay, so for we saw that by a theorem of Brendan, this basis generating polynomial is stable implies we have this specific negative dependence. And then we also saw by a matrix tree theorem that if the matrix is graphic, well, yeah, matrix tree theorem, basis generating polynomial is stable. Maybe I should. Matrix tree theorem using the fact that these polynomials are determinantal. Determinantal implies stable. Okay, determinantal implies stable. Stable implies this negative dependence. So, well, why do people? So someone asked me at dinner, why do people care about negative dependence? And you can look up. There are many reasons that people, and especially in application, people who study probability, care a lot about negative dependence, and I won't get into that. I don't know too much about it, to be honest, but you can read about it. They come up machine learning, sampling, and computer science, and combinatorics. They come up a lot. So today I will show you just one specific consequence in terms of these log-concave sequences, why negative dependence implies a log-concavity. Right, so this is sort of a motivation. Okay, we'll see something stronger later on, but we'll see negative dependence implies log-concavity of number of independencies. So before I get there, maybe let me set some notation. So for a matrix, let ik, so matrix on an element like this time. I let ik be the number of independent sets. So if you're thinking of graphic matrix, so we'll talk independent sets are a collection of edges without cycles. So in other words, they're forests. So we're looking at number of forests of size scale. Okay, so in a uniform matrix, these are just going to be n choose k. If k is small enough, right, when k is large, then it's going to be 0. So the question, or so Mason's conjectures, non-theorems. So write down a weak version and a strong version. So a weak version is that this sequence of numbers is log. Plus 1 for k, for all the k's that make sense, going up to rank -1. And then this is the weak version. The strong version is with this Newton-like denominators. So this kind of inequality is called log-concave. You can see that if you take the logarithm, that means that, logarithm means that 2 times the middle one is bigger than or equal to the value at the 2 points, right? The middle one is bigger. So that means that if you take the logarithm, right, it looks like, right, the middle here is k -1, k, and k plus 1. So concave means that the midpoint is higher than the average of the endpoints. Okay, so if you take the log, it's going to be a concave. And then this, the second one is ultra log concave. Okay, or Newton-like inequalities, right? And then this is stronger because the denominator here is bigger than the product, which follow from the log-concavity of the binomial coefficient. So I will explain, briefly explain why negative dependence, if we do have negative dependence for all matrices, which we don't. Okay, so if we do, then it would have implied log-concavity of independent sets. Okay, so one way to see this is as follows. You could maybe, I could rewrite this. You saw this in our exercise yesterday that we can rewrite this at an equivalent formulation. So instead of writing like this, I could write probability of I in B, J not in B, times probability of J in B, I not in B, going to be equal to product of both I, J, and B times probability of neither is in. So it was part of the last problem. Has anyone done that?
The first term should be J not.
Oh, sorry, J. This one, thank you. Yeah. This is actually just algebra. You could say I could name this quantity A, name this quantity B, name this quantity C, and name this quantity D. Right, so these are all things that you can have A plus B plus C plus D is equal to 1. Right, and then this quantity right here is I in B, and J can either be in B or not in B, so this is A plus C. Right, and then this thing is J is in B, I is either in B or not in B. So hold on, this is it B plus D? No, B plus C, right? B plus C. And then both I, J, I, and B, so this is C, right? And then you have to do some algebra to show that they are equivalent, also using the equation that A plus B plus D is equal to 1. Okay, so these are equivalent. Okay, now we're going to do this second thing, right? So assume that we do have negative dependence for all matrix. It's not true, but it's something that you do. To get the log-concavity, first you can reduce it to this log-concavity. First, let's just look at the case one. I'm looking at the end of my sequence, meaning my k plus 1 is the rank, and k is rank minus 1. So so to prove this implication, you first consider the case one. K plus 1 is equal to the rank. Okay, so we're looking at the end. You can always get into the case by something called Dilworth truncation. So it turns out that if you have a matrix, so you already also saw in the exercises, like if you look at all the independent set up to side K and you forget about all the higher independent sets, they form a basis of a truncated matrix, a new matrix. So using something called Dilworth truncation. So we saw the word Dilworth all the time in the dining hall. We can reduce to the case 1k plus 1 is the rank, okay? And now you take your matrix, and then what you do is you add in two new free elements called I and J. So as what you do is add in free new elements, I and J. What it means is that if you're thinking about vectors, the intuition is that the free elements means the sort of your generic random new vectors in your vector space. So what it's going to do to your basis is that the all bases are still bases, right? And then any one of these new free elements together with rank minus 1 independent set, they also will form a new basis. So that means that when you add in, say, if you add in, say, one free element I, so that means that the basis, the new basis of the new matrix, now you have a bigger ground set because you have all ground set together with the I, okay? And the basis are the all bases, right? Together with things that looks like I union some independent set of rank minus 1. That already exists, and you do that twice. You do that at a free element I, right? And then you do it again. All right, now you suppose you have negative dependence for this new matrix. Let's just write down what that means. Right? Let's count them. Okay. You always, probability. So you're always divided by all the number of bases. So we're just going to forget about it. Right? So that means that let's count the number of bases that contains I but not j. Right? So let's do number of bases that contains I but does not contain j. So a basis that okay, so you can ignore j, but the number of bases that contain i's are number of independent sets for rank -1, right? And then rank -1 is equal to k. So this is ik, right? And similarly, the other term on the left-hand side, number of bases that contains j but not I, is also ik. Okay, but on the right-hand side, the number of bases that contain both I and j, right? Then they are going to be the independent sets of rank or size rank -2, which is k -1. So this is ik -1. And then number of bases that do not contain either I or j. So these are the original bases. So this gives you ik. And that gives you the log-concavity. So this is yeah, so I learned this from a paper of John. I think this was known before, but it's so this is one sort of give you intuition for why people study negative dependence in an attempt to prove these Mason's conjecture. Right? So you can play around with other things. You can look at other probability distribution, maybe not as uniform, like other stuff. Right? But it doesn't quite work out. I mean, yeah, as you saw in the exercises, we don't always have negative dependence. Okay. So we're going to move on. So today, the point of today's lecture is that we're going to replace real stability with log-concavity, not in the sense of log-concavity of coefficient, but actually log-concavity as a polynomial function. Right? So there are two types of log-concavity appearing in this lecture. So just to acknowledge that they're actually different. Okay, so right here we've been talking about log-concavity of a sequence of numbers. Okay, so right now we're going to move on to talking about log-concavity as a function, as a real value function. So, sorry? K plus one. Oh, k plus one, thank you. No, wait, yes, k plus one. Rank is k plus one, thank you. Yeah.
May I ask, so this full statement for which matrix?
Oh, this is, okay. If assuming that, yes, that's, no, this is for which matrix, yes. So, sorry, that is one of my downfalls is that I don't write everything, okay. So I start with the matrix M, and then I do I added two free elements, okay. And then I am counting in the new matrix, I'm counting the number of bases in the new matrix. So in the new matrix, but the i's refer to the old matrix, okay, where the right I k -1 I k, yeah, sorry, this is confusing, +1 or number of independent sets in the old matrix, independent sets in old matrix. Does that make sense? Yes.
Thank you.
Okay, we start with the old matrix. We're interested in counting the independent sets. And the way you can do is by adding these free elements and count these bases that contain I and not I in the new matrix. So negative dependence will translate to this concave inequalities for the independent sets. Okay, so let me move on. I thought I dropped this. Okay, so today. So yeah, so all these implications I wrote down, they're all nice, but the thing is that they're not true generally. Okay, so today we're going to give up on stable polynomials and replace stable with log-concavity. Right. So let's look at a polynomial. So for the rest of today, all my polynomials are going to have non-negative coefficients. Okay? Even if I don't write it, we're going to assume that the polynomials have non-negative coefficients. So we say that f is log-concave. As a function, its logarithm is a concave function. So it is log-concave on the positive orthant. We don't want to take lots of negative. Right? So because f has positive non-negative coefficient, right, it is non-negative on the positive orthant. Positive on is actually positive on the positive orthant. We can take the logarithms, right? If the log f function, right, is concave. Okay, now we have to pretend we're back in calculus 1 for a bit. Okay, let's imagine what it means to be concave. Right, so in calculus 1, well, maybe even before we get to calculus, concave, the picture looks like if you have 2 points, A and B in Rn, right? If I'm drawing the graph of my log f, it has to look like that, right? More precisely, what it means is that if I have my function values, right? So this is my log f of A, log f of A. If I take sort of convex combinations of these 2 function values, they have to remain lower than the values at the convex combinations. Okay? So if I take a point in the convex combination, looks like lambda A plus 1 minus lambda B, right? So some point along the line. So that means that if I look at the convex combination upstairs, so this is the convex combination of my values, has to be less than or equal to my log f of lambda A plus 1 minus lambda. Okay, this is what concavity meant for every 2 points, A and B in Rn plus. All right, and then we could exponentiate it, and then you can also write this as, so you have f of A to the lambda times f of B to the 1 minus lambda, right, is less than or equal to f of lambda A plus 1 minus lambda. Okay, so this is from the definition. What is going to be useful for us is the second derivative test from calculus 1. Equivalently, so if you look at all direction V, right, so you can think of directions of the difference between my 2 points, right, for all directions. Right, so the derivative, the second derivative in that direction of log f is less than or equal to 0 for all x are okay, so second derivative test. Yeah.
So in your expression for log concavity, is the 1 minus lambda supposed to be multiplied by the b, like instead of 1 minus lambda times b?
Oh, yes, parenthesis missing. Thank you. Yeah.
And also in the picture.
Oh, in the picture as well. Thank you. Let me see. 1 minus, yes, thank you. Yeah. Yeah, if I vary lambda, I'm moving between A and B. I have to I below the function. Okay. So we have to check that, right? Another way to look at it is that the second derivative is less than or equal to 0 at every point. So now let's look at the second derivative a little more closely. So what does it mean by definition? I'm looking at V1 partial 1 plus Vn partial n. So V1 through Vn are the coefficients are the coordinates of the vector v, right? So I am doing the rational derivative 2 times, right, of log f. And then if I just multiply out, it's going to be sum over VI j of partial I partial j log f over all ij's. And then I can write this as a matrix multiplication. This is actually a matrix Hessian. So this is a square matrix whose ij entry is the partial derivative, partial I partial j of log f. Right, and then you're multiplying with factor v, transpose right here, and vector v right. And we're saying that this has to be less than or equal to 0. So that means that this matrix in the middle is negative semi-definite, right? So this matrix is denoted, this is the Hessian, is denoted, I don't know how to call this, upside down triangle. Hessian, nabla. Log f. Yeah, so we need this to be negative semi-definite, right, for all x in the positive. Yeah, so if you start with a polynomial, right, and then if you compute this this Hessian, this is going to be a matrix, a symmetric matrix whose entries have variables in it, whose entries are polynomials. Okay, because if you take the logarithm, if you take the derivative of logarithm, right, become rational functions. Okay, so that the entries are going to be polynomials, and then so it is negative semi-definite for all x. So what it means is that one way to check this is, all the eigenvalues are non-positive, all the principal minors, right? So if you look at okay, all the eigenvalues are non-positive. Okay, so and also check in. So that is sort of a lot of sort of polynomial algebra if you want to prove such a thing, right? Because you have to prove it for all x. So we're going to look at it more closely later, but first let's look at some examples. So example, so if you have a univariate real-rooted polynomials are log-concave. So we can look at it directly from the definition. So real-rooted, so that means that I can write it, I can factor it as a polynomial like this. And then let's look at the logarithm. So, log of the product is the sum of the logs. And then if you take the derivative, so if you take dt, you get 1 over t minus ri. And then if you take the second derivative, you get negative 1 over t minus r squared. Okay. So this is always non-negative. Second derivative is non-negative. So these are log-concave. And in the homework, you're going to show that stable polynomials are log-concave. So I won't go through that. I will say. Stable implies from the definitions. So right now, the next thing I want to do is to rewrite this Hessian of the log f in to get rid of the log. All right. So let's see, to rewrite. Right, so each entry in the Hessian look like this, right? This is the entry ij. So we're just going to go back in calculus 1 and do the derivative. So we have, okay, so by chain rule, it is 1 over f times delta I.
What's a J?
Sorry, j. Okay, that. And then quotient rule. Okay, so this is what the entries in the Hessian of the logarithm looks like. So as a matrix, see, looking at this, what is the, so we can factor out 1 over f squared, putting them in the matrix, right? Factor out the 1 over f squared. And then the first thing is f, which is like a scalar, right, times Hessian of f. So f times Hessian of f itself without the log. And then the second thing, right, what is it looking like? And look at the second part only. What is this matrix, right? So this is each entry, right, is partial I times partial j. Okay. So it looks like a column vector times a row vector. Okay. So these are called the gradient. So it's the gradient. Right, so this is a column vector times the row vector, where gradient is just vector of partials. Right? So where and this is the Hessian. All right, we okay? So, okay, now we are reduced to studying, right, properties of this matrix. And we're interested in what happens when this is negative semi-definite. So here's a nice lemma, so that connects log-concavity to this matrices with Lorentzian signature. So which I love. Matrix with Lorentzian signature is a symmetric matrix whose the pattern sign patterns of eigenvalues are like, you know, all negatives and a positive, or all positives and a negative. So if f is log-concave at a point in the positive orthant, if and only if the Hessian at x equal a has at most one positive eigenvalue. Yeah, so this condition of having at most one positive eigenvalue, this means that this matrix has Lorentzian signature. So Lorentzian polynomials are defined using this kind of properties that certain matrices, certain Hessians of Hessians of derivatives has at most one positive eigenvalue. All right, so while F is log-concave means that this matrix right here, Hessian of the log, is negative semi-definite, right? And then this lemma is saying like not this whole thing, but just the first thing, right? Just the first thing. So this follows from at least one direction, follow from Cauchy interlacing. And if you haven't heard it, don't worry, I'll go through a proof of one direction. Okay? So, right, so the intuition is that, you know, this thing log-concave means that the first thing right here is negative semi-definite. So all the eigenvalues are not positive. And then right here, you're changing it by just a vector times its transpose, a rank one thing. Right, so it cannot mess up the eigenvalues too much, right? It will introduce at most one positive eigenvalue. Okay, so that's the intuition, that is the Cauchy interlacing. But maybe let me also maybe draw a picture just to so that for more better intuition. So yeah, so let's do the proof in one direction. I think the other direction is a bit more involved. Okay, so for that, F log-concave, right, implies that this entire matrix, so is, let me just write it down, is negative semi-definite. That means that if I write down this whole thing, right, plug in x equal a, this is negative. And if you look at this quantity, so if you are, maybe another way to think about this is, you know, you are this thing is negative semi-definite. And this one, if you look at the hyperplane perpendicular to this vector, right? So if you restrict to the hyperplane, adding this extra thing doesn't change anything. So maybe to be more precise, if you look at the vector satisfying, it's like if you look at vectors perpendicular to, you know, the gradient, then the second thing doesn't change, right? Doesn't change the quadratic form. And then you can, so you're reduced to looking at the first one. So this means that this, in my case, the transpose, and that FA is just a positive number. So I'm gonna ignore that. Okay, so we transpose to square. Okay. It's non-negative. So it is still, right, negative semi-definite on the hyperplane perpendicular to the gradient. And then that hyperplane, so I'll draw a picture. So you have some kind of a quadratic form. And then you have a hyperplane. So this hyperplane is not meeting the positivity region of this, right? So if you restrict to the hyperplane, it is not negative, right? So if you have a quadratic form that is, say, positive here and negative here, right? And then if you slice with the hyperplane, it's not meeting the inside of the cone. It's not meeting the positive region, it is in the negative region. So this, they meet only at the origin. And so this actually implies that if you look at the span of all the positive eigenvectors, right? The span of positive eigenvectors cannot meet the hyperplane. Okay, so the span of positive eigenvectors of Hessian of F, okay, cannot meet that hyperplane. Cannot meet hyperplane, which is perpendicular to the gradient. Cannot meet the hyperplane. Perpendicular to the gradient. So that means that there is at most one positive eigenvector.
Can you explain again where the second implication came from?
Yeah, yeah, because
The second.
this one.
Yeah.
Oh, this one is saying if my V is such that the second quantity is 0, then the first quantity is less than or equal to 0, right? I'm choosing the V such the second quantity is 0.
The true singular V.
If this is second quantity, sorry, I should have put a parenthesis, okay. This thing, sorry, okay.
Oh.
Yeah, I missed the parenthesis, that changes everything, thanks for the question, okay? Right?
Could it be an f of a multiplied?
Yes, f of a is a positive number. So, yeah, it should be multiplied, but I just factor it out because it's a positive number. Okay. Yeah, good question. Okay, so there should be a f of a, but it is positive, so I acknowledge. Okay. So this is sort of intuition behind how things connect to this Lorentzian signature. Okay, actually, I'm going to move on and actually get to the definition of these completely log-concave polynomials or Lorentzian polynomials.
Can you explain the last implication again?
Last implication again? Yeah, that's right. So I'm looking at, or maybe how about this? If the span of positive eigenvectors, it meets the hyperplane, that means that I could write a vector that is a linear combination of positive eigenvectors, right? And then if this lies on the hyperplane, then that means that if I just write this thing out, I'm going to get a positive number. If this V is a positive, linear combination of positive eigenvector, this quantity is going to be positive.
And how does it relate to the picture?
Okay, so the picture is, let me see. So this is a function of V, so this quantity right here, okay? As a function of V, this is it's a quadratic form in the function of V. And then this statement is saying that there is a hyperplane. If you restrict my function on the hyperplane, the function is not positive on the hyperplane. So here's a picture, right? So in the quadratic form, the function is positive inside the cone and negative outside the cone. And there's a hyperplane that lies in the negative region. Yeah. So now we get to a definition that we have been promised. So that, again, as we are polynomial with non-negative coefficients and homogeneous of degree D. So we call F completely log-concave. Or CLC if any collection of vectors in non-negative directions, this repeated directional derivative is log-concave on the positive. Right, so it's not enough that the polynomial itself is log-concave as a function. All this partial derivative, and then again and again and again, the all has to be log-concave. Of course, I mean, if k is large enough, it's going to be 0, or it's going to be linear. If linear, then this is log-concave, right? So that's the definition. And so this was. Let's see. Give some credit to the authors. I don't know where they are. Okay. So this was this definition is due to Anari. Always Baran. Okay. I don't know. Maybe Tracy correct me if I'm spelling it wrong. Vincent. And then some of them was also joint work with Liu. So they have a series of 4 papers where they study this property of the various things about this polynomials and show its implications in matrix theory and combinatorics and computer science. Yeah, at the same time, we also have Peter Brennan and Jen He. They came up with this what they call Lorentzian polynomials. And they also prove many things about Lorentzian polynomials, that the definition is different. Definition of Lorentzian polynomial relies on these Lorentzian signatures and derivatives. I mean, for the quadratic form, having Lorentzian signature, and it's kind of recursive. Just look at polynomial whose derivative is Lorentzian and so on, and then you have to take some kind of a closure, right? So, but it turns out that these are equivalent. So you can find a proof in this Brendan He paper that completely log-concave is equal to Lorentzian. So although the definitions look different, set of polynomials are the same. Yeah.
Do Lorentzian polynomials have to be homogeneous?
Yes, I believe so. I mean, you may be able to extend it, but yeah, at least the original definition, they're all homogeneous.
You have a typo in Cynthia's name. It's her.
Okay, well, this one name I should not mess up, but
I
okay.
think it's GH or always
Sorry, always GHA.
GHA.
Okay, yeah, always Garan is one person. Yeah.
Also random.
Is that okay?
Right.
I wrote it down somewhere, so I just cannot find it. Okay, yeah.
First name is N and Pepper
Random.
Brandon.
Sorry, Petra.
Brandon.
Brand. Is that right?
Anari was right.
Okay, yeah, sorry. And Brand Day. Okay, yeah, it's not Brandon Her, it's not, Petra Brandon and Jenna. Okay. Yeah. So, okay. So stable polynomials are completely log-concave or Lorentzian because you have a. Okay, let me. Because I mentioned earlier that stable polynomials are log-concave, and then the derivatives of stable polynomials are again stable. So they are again log-concave and so on. Okay. So stable polynomials are log-concave and completely log-concave as well. All right, so maybe the last thing I'll do today is go back to the coefficients, right? So right here, we have been talking about the polynomials being log-concave. But then we started with saying coefficients of these real-rooted polynomials being ultra-log-concave, right? So it turns out that the polynomials being Lorentzian implies that the coefficients are ultra-log-concave. So there is a connection, right? Also, I should mention that before all these, before the completely log-concave and Lorentzian, people have studied, so Gurvitz, so I'll write down the name, has studied something called strongly log-concave. So which is where instead of looking at directional derivative in all positive direction, Gurvitz only look at directional derivatives in the coordinate directions. So called strongly log-concave. And of course, a priori it is weaker But it was proven in, say, Brenda and her paper that they are all equivalent, actually, strongly log-concave, completely log-concave, and Lorentzian. So actually, and with a theorem, I think it is actually going back to Govis. Is about Newton's inequalities, Newton-like inequalities for completely log-concave, Lorentzian. So we proved it for strongly log-concave, but then it implies complete log-concave and Lorentzian polynomials. So what it says is that if F, I'll write it as a homogeneous in two variables. So that we can talk about a sequence of coefficients. Have a homogeneous polynomial of degree d in two variables, and it is completely log-concave, strongly Lorentzian. If any of these equivalent conditions are true, then its coefficients satisfy ultra log-concavity conditions. Yeah, so I think I have time to go through the proof. It's just a straightforward calculation, but let's do it together. So the proof is by you differentiate it down to a quadratic form. And that's going to be the theme of my Thursday's lecture, is that you can do a lot of things by taking derivative all the way down until the degree 2. Right, so this is the proof. Okay, so you're going to take, so we're interested in proving this, right? We're fixing a k. K somewhere between 1 and d minus 1. Okay, and then we are taking derivative all the way down to the following. So let Q be k minus 1 with respect k minus 1 times with respect to the first variable, and d minus k minus 1 times with respect to the second variable. And you get this. This is a degree 2 polynomial. And it still has positive coefficients. So I'm assuming that everything is positive coefficients. Now let's see what the relevant terms are, right? We're interested in this 3 terms. So let's see what are the coefficients of these 3 terms after I take the derivative. So before the derivative, right? So relevant terms before the derivatives are f look like something, right? Plus c k minus 1 x to the k minus 1 x2 to the d minus k plus 1 plus ck x1 to the k x2 to the d minus k plus ck plus 1 x1 to the k plus 1 x2 to the d minus k plus 1. So these are the relevant terms. And then after I take the derivative, so I take this one, you differentiate with respect to x1, k minus 1 times, so x minus 1 is gone, right? But you pick up k minus 1 factorial. And then you have x2 squared.
Also pick up the factorial for next two.
You also, sorry?
Also pick up some sort of factorial factor.
Oh, yeah, that's right. Yes, that's right. For the second one as well, that's right. You have to differentiate this d minus k minus 1 times. So, but you started with d minus k plus 1, right? And then you do the following factorial all the way down, but you know, it's not the factorial. The only thing you're missing is 2 and 1. Okay, so you have that times x squared. Okay, maybe I'll stop talking and you can do it on your paper and we'll check.
Coefficient is CK minus 1. No?
C k minus 1, thank you. Okay. Plus. Okay, so for the second one, yeah, so it is ck, and then I do have k factorial minus k factorial x1, x2 plus the last one is ck plus 1, and similarly from the it's like k plus 1 factorial, but I'm missing the 2 and the 1 times okay, so I have this quadratic form.
The first thing would be like x.
It is x2, thank you.
But then the first
So
term.
the first one, this is x1, thank you.
It goes-
No, is it the other way around? This is x2 and this is x1. Okay. This quadratic form is log-concave. So. So Q is log-concave by definition, by assumption, implies that the Hessian is a 2 by 2 matrix. Okay, this 2 by 2 matrix has at most one positive eigenvalue. Right, but it cannot have both eigenvalues negative because that one means that it is negative definite. But you can see that it is a quadratic form with positive coefficient. It's not going to be negative definite. Okay, or you can see that the trace is positive, so it has to be exactly one positive eigenvalue. Okay, so this means the determinant, but cannot, let's say that, but at most one, but actually, but cannot be both negative. Okay, so maybe I won't write that down. So this determinant is negative. Okay. So let's write down the matrix. Let's write down the Hessian is going to be the plus 1 factorial minus k minus 1 factorial ck plus 1. Yeah, so this is the derivative, second derivative with respect to x1. So this cancels out the 2 in the denominator. Okay. Yeah, so times d minus 1 factorial ck. Okay, so these are the second derivatives of the quadratic form. And this one, the determinant has to be negative. And then I could factor out d factorial squared from a lot of them. Then if you factor out d factorial square, I could rewrite this as this is ck plus 1 divided by d choose k plus 1. Yeah, so you can check that you can move this in the denominator of the denominator, right? Okay. So this is exactly what you want. Yeah, so the determinant is less than or equal to 0, and that proves the Newton's Newton's-like inequalities or ultra log-concavity. Right, so this one, the determinant is that like the 0 implies. Okay, so I'm just out of time for today. So next time I will talk about how to some easier way to prove that polynomials are Lorentzian. And then also the matrices are going to come back in two ways. One is that it is helpful to know that the support of the polynomials are matroidal, like you have heard of M-concavity or generalized combinatorial is important that these supports have the matrix structure. Another way that matrices are going to come in, and we'll see that these basis generated polynomials are going to be Lorentzian. Okay. Right, so we'll tie back log-concavity and matrix back together on Thursday. Yeah, I thought there's a question.
Yeah, could I ask, so I can also ask after, but like, could you go over again why the determinant of like nabla square 2 is less than or equal to 0 is implied from the previous statement?
Yeah, that's right. Okay, maybe let me write a little more. So it has at most one eigenvalue, but it is not negative definite. It cannot have two negative eigenvalues. If it is, yeah, it's non-negative definite because it's a polynomial with all the positive entries.
Oh, so it in fact has exactly one positive eigenvalue and therefore the product of the eigenvalue must be.
That's right, exactly one. Well, it can be degenerate with 0. Yeah, but yeah.
Wait, so why can it not be negative semi-definite?
Negative, yeah, so it cannot be negative definite, it cannot have two. So it's a quadratic form, it is negative definite means that all the values are negative. But you can see that, or maybe another way to, maybe easier way to say this, as a polynomial, the trace is positive, so it is a positive.
Right, because the sum of them is positive, but the product.
That's right,
of them is
yeah.
like- Yeah, okay, that makes sense, yes.
Is the motivation for considering like a polynomial in x1 and x2 just like two variables in order to prove? Is there like a generalization?
Yeah, so you could do various, like some kind of change of coordinates for that if you want to, maybe. Well, okay, to be able to talk about, this ultra log-concavity, I just want like a sequence, right? So, but if you want to, maybe are you asking like, what if I want to, well, okay, and if you have many variables, right, you can do things like variable substitutions, or you can take the derivatives and, right, things like that to, you can look at the sequence of coefficients in some other directions as well. Is that what you're asking for?
Yeah, just like if you had more variables in F, like here we only have x1, x2.
That's right. You can talk about, I think if you remember from Chris's talk yesterday, I think he talked about kind of like log-concavity like along like different directions. Then you can use this to prove that kind of thing. Yeah, and in some other different directions. Using different operations that you can do on this polynomials, or to reduce it to the two variables.
Does this help us to prove the stronger mesons?
Yes, yeah, that's right. You're looking at, yeah, this will follow. So this will follow from the fact that, so I don't know in what detail I'll discuss, but the result is that the independent set generating function, right, of a matrix is Lorentzian. So if I look at, if I look at this polynomial where CK is IK, that is Lorentzian. So that's a theorem. So next time I'll discuss a bit about how does one prove that something is Lorentzian, right? Because right now, by definition, you have to check so many, for all V, for all X, for all that. But I'll say a bit more about like easiest way to get a handle on that, and then mention the results about Mason's conjecture. Yeah, so so the strong Mason conjecture was proved simultaneously by those team of Anari, Oves, Goran, Liu, and Van Zan, and also Brendan and her. Yeah,
I was gonna just clap for you, sorry.